Okay, this is MA 161's exam 3 from, looks like this is spring 2019. This is actually my first exam 3 that I'm recording, so hopefully this goes all right. I took a little peek ahead at the questions, and it's mostly just applications of derivatives. So a lot of finding maximums and minimums and the critical points and, concavity, things like that. So hopefully this shouldn't be too bad. Um, Oh, okay, this is a great example of that. So question one, the graph of the velocity function of a particle is shown below. So this curve here, it's not the position of the particle, it's the velocity of the particle. Um, and on what intervals is the particle speeding up? Okay, so speeding up, that is keyword for the velocity is increasing. So when it's speeding up, it means the velocity is going up. It has a positive acceleration. And that's pretty easy to find in this case since we're given the velocity function. So in order to find the intervals where this particle is speeding up, we just have to find the intervals where this curve is going upwards, where it's increasing. So it's going to be intervals like this. You can see that line is going up and up and up until looks like this point here at x equals 2. And then it's going to have another interval here at x equals 4 all the way to infinity. So if I'm not mistaken, that should be our answer. Our two intervals should be, looks like maybe 0 to 2 and then 4 to infinity. Those should be our two. It's not. Okay, I think the answer is actually D. Okay, I think I know why that is. So they asked for when it's speeding up, which is technically different than when the velocity is increasing because speed is the absolute value of velocity. So if that really doesn't make a difference for this portion of the graph, but when you look at the bottom half, when you take the absolute value of it, that's going to look like this. So imagine this line here is just the absolute value of this. And that doesn't fit the needs of this problem since this line is now, going downwards. It's decreasing. So that interval there isn't really going to, I guess, count for this problem. So I guess in this case, the interval is actually going to be from 1 to 2 instead, which is that little segment there is when it's speeding up. So I guess that's how they got the answer of D for this problem. Question 2, this is just a derivative problem. So we're given our f of x, which equals cosine h of sine h of x, and we need to find f prime of x. So these are, in case you didn't know, these are hyperbolic functions. There's 6 of them, and they correspond to the 6 trig functions that you already know. They just have h's at the end of them, so we have cos h and sine h here. And the cool thing is the derivatives of these are, they're not equal, but they are very, very similar to the derivatives of all the regular trig functions that you already learned for the exam 2 stuff. So the two that we have here, cosine and sine, so derivative of sine h, derivative of sine h of x, that's going to be equal to cosine h of x. And this is the part where it diverges a little bit. Cosine h of x, its derivative actually equals positive sine h of x. And I do not need that there. So normally, derivative of cosine is negative sine, but in this case for the hyperbolic functions, there's no negative. So that's what we do for this. So doing our derivative now, looks like the first thing we do is take the derivative of this outside cos h here. That would become sine of h. So f prime of x equals sine h of the inside, which is sine h of x. And then we do have to do chain rule since we have an inside portion here, which multiplied by the derivative of the inside, derivative of sine of h, no, derivative of sine h of x, that's how it's pronounced, that is just cosine h of x. So that should be our answer. Yeah, E, that is the answer here. That's how you do derivatives of hyperbolic functions. Question 3. A certain bacteria culture grows at a rate proportional to its size. If the size of the culture doubles every 7 days, how long in days does it take for the initial size to triple? All right, this is an exponential growth problem. For all of these, we use I would call it the PERT function because you have the size of the population after t, in this case t is days, so after t days, that's equal to the principal amount, which is how much it starts at, times e to the r times t, where r is our rate and t is the amount of time. This is why I call it the PERT function, because it spells out PERT. So for this one, let's substitute in what we know based on how this problem starts out. Looks like we know two things. A, that it takes 7 days, and B, after 7 days, it doubles. So on the left-hand side here, we can replace this with 2 times P, since it doubles after 7 days. We can just do 2 times the principal. That equals principal times e to the r. Oh, not r. T is going to be 7 because it takes 7 days for that principal to double. That is a crappy 7. Let me rewrite that. 7r. There we go. So now we have this. We do have 2 different variables, but fortunately these two are actually just going to cancel each other out if we divide by that. And after that, we'll only have one variable, r, and we can go ahead and solve for it. So doing that, let's see, divide both sides by p. We'll get 2 equals e to the 7r. To get this 7r all by itself, we can take the ln of both sides. So this will become ln of 2 equals the ln of e to the 7r. And when we do that, we can use a property of logarithms. We can take this 7r, move it out front. We'll be left with ln of 2 equals 7r times ln of e. Now ln of e is just 1, so we can cancel that out. And we can divide both sides by 7 to get r equals ln2 all over 7. So that is the rate that we're given. That's the rate. I guess it's every 1 day. I don't really know what the rate means. That's just the variable that we have now, and using it, we can go ahead and solve for what we're actually supposed to find, which is how long it takes for the population to triple. So setting up a new equation, we want the population to triple, so we're going to do 3 times p on the left. That's going to equal the principal times e to the r. So r we found now. That is ln 2 over 7. And this is all times t. And this t is what we're trying to find. We're trying to find how long in days. So same thing as before, we can divide both sides by p to get 3 equals e to the ln 2 over 7 times t. And we only have one variable to worry about, and it's the one we're looking for. So we can just solve for that, and we'll have our answer. So same thing as before, we could take the ln of both sides to get this top exponent all by itself. This will be ln of 3 equals ln of 2 all over 7 times t times ln of e. Ln of e, again, is just 1, so we can forget about it. It's so hard trying to not make your t's look like pluses, but that's a t. So we have this now. We can go ahead and divide both sides by ln 2 over 7 to get our answer. So dividing by fractions is the same as multiplying by the reciprocal. So this is going to become ln 3 times 7 over ln 2 equals t. So we know that t equals 7 ln 3 over ln 2. Answer choice C. Question 4. We've got a nice related rates problem. So we have a rectangle. The length of the rectangle is increasing at a rate of 8 centimeters per second, and its width is decreasing at a rate of 3 centimeters per second. How fast in cubic centimeters is the area of the rectangle increasing at the moment when the length is 20 centimeters and the width is 10 centimeters? That's a lot of words and information thrown at you, but this problem is not so bad. first off, for these related bridge problems, the first thing you always do is identify which formula you should use to solve this with. Usually, the formula you use incorporates a lot of the different, pieces of information that you're given in the question statement. So it looks like since we're trying to find area, excuse me, and we're given length and width, we should probably just use the regular, area formula where area equals length times width. That would probably work. So using this formula, we can go ahead and take its derivative, and we'll get an answer with a whole lot of d over dt's in it. So taking the derivative of this left-hand side, a, that is just dA over dt. And on the right side, well, we've got two things being multiplied together, so we should probably use the product rule. Excuse me. So on the left here, we're going to have the derivative of L, which is dL over dt, times W, plus L times the derivative of W, which is dW over, oh, that is a weird W, dW over dt. So that is I don't really know what the best way to explain what this is, but I'm just going to call it the derivative of the area equation. So we have this now, and we have a whole lot of new variables. We've got dA, dL, and dV over dt. But the cool thing is we're given most of them. So for example, dL over dt is going to be 8, and dW over dt is going to be 3. So if we go ahead and plug in those values along with the weight or the width and length that we're also given, we should only be left with dA over dt that isn't filled in. We can just go ahead and solve for it. So we're asked to find dA over dt, so that's going to be left standalone. We're not going to touch it. Now on the right, so dL over dt, that is the rate at which the length is changing. They give us that. That's 8. So we plug in 8. The width, just the standard width at that moment, is going to be 10. So we go ahead and plug in 10 here, and then plus L, that's just the length at the moment, which is 20 centimeters, and then dW over dt, that's the rate of the width, and that is, I think it's going to be -3 because it's decreasing. We can go ahead and check our work afterwards if it's supposed to be positive, but I think it's going to be negative just because it's decreasing. So now we have this, and we can just go ahead and solve for d over dt by multiplying these two little things. 8 times 10 is 80. 20 times -3 is -60. We're left with 20 is the rate at which the area is increasing when the length is 20 centimeters and the width is 10 centimeters. Answer choice E. Question 6. Use a linear approximation to estimate the value of e to the power of -0.01. So for linear approximation problems, we've got a great formula that we use for this. It is f of x is approximately equal to f of a plus f prime of a times x minus a. So in this case, a is going to be a value that is really close to what we need to plug in. So since the value that we should be approximating this with is -0.01, a number that is really close to that would be easy to substitute in would probably be 0, since it's really close to -0.01. So that is going to be our a value, 0. Our x value is going to be the original, which is -0.01. The only thing left to find before we start plugging in numbers and equations into this formula is what our f of x should be. Now the f of x is just what the original problem was, but you substitute the approximated value with x. So in this case, we're just going to write e, and then in place of that -0.01, we put an x. So that is our f of x, and we can begin solving this problem. So this approximately equals f of a, so we determine that a is going to be 0, so we just write e to the 0, and then plus f prime of a. Now the derivative of f of x, that's going to be, derivative of e to the x, which is also e to the x, so this is also going to be e to the 0, and this is times x minus a. So x is -0.01, and a is 0. So we have this, and now we just simplify. So this approximately equals e to the 0 is 1, e to the 0 is 1 again, so this is going to be 1 plus the quantity of negative 0.01, and this approximately equals, so 1 minus 0.01 is 0.99. Answer choice D. Question 6. Use a linear approximation to estimate the value of e to the power of negative 0.01. So for linear approximation problems, we've got a great formula that we use for this. It is f of x is approximately equal to f of a plus f prime of a times x minus a. So in this case, A is going to be a value that is really close to what we need to plug in. So since the value that we should be approximating this with is negative 0.01, a number that is really close to that would be, easy to substitute in would probably be 0, since it's really close to negative 0.01. So that is going to be our A value, 0. Our X value is going to be the original, which is negative 0.01. The only thing left to find before we start plugging in numbers and equations into this formula is what our f of x should be. Now the f of x is just what the original problem was, but you substitute the approximated value with x. So in this case, we're just going to write e, and then in place of that negative 0.01, we put an x. So that is our f of x, and we can begin solving this problem. So this approximately equals f of a, so we determine that a is going to be 0, so we just write e to the 0, and then plus f prime of a. Now the derivative of f of x, that's going to be, derivative of e to the x, which is also e to the x, so this is also going to be e to the 0, and this is times x minus a. So x is negative 0.01, and a is 0. So we have this, and now we just simplify. So this approximately equals e to the 0 is 1, e to the 0 is 1 again, so this is going to be 1 plus the quantity of negative 0.01, and this approximately equals, so 1 minus 0.01 is 0.99. Answer choice D. Question 7. Find the absolute maximum and minimum values of the function f of x equals cosine x plus sine x on the interval from 0 to pi. So this is an absolute maximum and minimum question, so we need to find our critical points. To find critical points, you just first you take the derivative of the function you're given, f prime of x, and then set it equal to 0, and then solve for x. So taking the derivative of derivative of f of x, derivative of cosine, which is going to be negative sine x, derivative of sine is plus cosine x. So there we go, we have our derivative, but we have a problem when we go and try to solve for the values of x that will make this equal to 0, because both sine x and cosine x are periodic functions. They go like this forever. So there's going to be an infinite number of critical points, an infinite number of points where the slope is equal to 0. So that would be a problem if it was just asking for the absolute maximum and minimum values across the entire function, but fortunately, this is just over an interval from 0 to pi, so we are able to actually find these maximum and minimum values. Now, what those values actually are, since we can't really solve for x, no, actually we can, I'm sorry, we can solve for x, we can just add sine x on both sides to get sine x equals cosine x, and then just figure out what values of x will make sine and cosine equal to each other. Now this is unit circle stuff. If you want to break out that big table of unit circle inputs and outputs, that's a fine way to do this. I like to do it visually, so I'm going to go ahead and draw out the unit circle and show you how I like to solve these. So we have our unit circle, 0 and 2 pi. Pi is over here. And when we want sine and cosine to equal each other, remember that for any angle, sine is this length here. This is sine. And cosine is this length here. This is cosine. So if we want those two lengths to equal each other, this angle here has to be basically in the position it is in right now, where it's at sort of a 45-degree angle, an angle of pi over 4. Any other angle, like let's say it was like this, the sine is going to be pretty big, it's going to be pretty close to 1, but the cosine is going to be pretty small and close to 0. So the only way that sine and cosine can equal each other is if this angle is right in between 0 and pi over 2, which is pi over 4. Now, we also have another angle down here where we have this length and this length, but that is actually outside the scope of our problem because this angle is 5 pi over 4, and that is bigger than pi, which is the limit. No, what's the right term? I don't know. It's outside of the range we're trying to find this at. So 5 pi over 4 is too big, so we don't need to worry about it. The only angle that we need to be concerned with this problem is pi over 4. So that is the point at which we have a critical point along this interval. Now to find if those critical points are maximums and minimums, we can go ahead and do this table thing. I don't know if they still teach this, but this is what I learned in high school, where you have x and f of x. And then on the left here, we're going to have pi over 4 in the middle. That's our critical point. Since this is an interval, we're going to put those two endpoints on the top and bottom, so 0 and pi. And then in between those two endpoints and pi over 4, we're going to put some intermediary values, some values that will be pretty easy to evaluate f of x for, but are still in between each of these values. So between 0 and pi over 4, maybe we could do pi over 6. That's pretty easy to plug into trig functions. And then between pi over 4 and pi, we could probably do like pi over 2, or maybe 2 pi over 3. That would also be pretty easy to plug into sine and cosine. So now that we have these 5 values, we can go ahead and evaluate each one of them in f of x, and we'll see what we get. So plugging in 0 into cosine x plus sine x, that's actually, I'm going to write it down here for ease of, you can see it easy. That's going to be cosine of 0 plus sine of 0. So cosine of 0 is 1, and sine of 0 is 0. So this is going to equal 1. So we put 1 right there. F of pi over 6, the next value we have, that's equal to pi over, shoot, what was it? It's a half, right? Okay, so cosine of pi over 6, that's going to be root 3 over 2, and then sine of pi over 6, this is 1/2. So this is equal to 1 plus root 3 over 2. Yes, that is the answer. Cool. And then we have our original one, f of pi over 4. That's our one and only critical point, which does make me a little concerned because usually when you find both a maximum and a minimum, you're going to need at least 2 critical points, but I guess you don't need it in this case since it's just an interval. Maybe one of the endpoints is going to be a maximum or minimum. So f of pi over 4, this is what we said before. Cosine of pi over 4 is root 2 over 2, and sine of pi over 4 is also root 2 over 2. That's kind of what we proved earlier with the unit circle. That's pi over 4 is one of the only arc angles that makes sine and cosine equal to each other. And this is going to equal to root 2 over 2. In other words, root 2. Now we have f of pi over 2. This is equal to cosine of pi over 2 is 0, and sine of pi over 2 is 1, so this equals 1. And then I'm running out of room. F of pi, our final value over in the table, this is equal to cosine of pi, that is -1, and sine of pi is 0, so this equals -1. So we have our 5 values now. We can, I should have been filling these into our table. This is 1 plus root 3 over 2. This is root 2. This is 1 and -1. Awesome. So So the only section is this one for things that are easy to visualize in your mind, but you should see that root 2 is the largest value we have here. It's bigger than all 4 of the other values, so that makes it pretty clear that this critical point is a maximum. That is one of the that's a local maximum among this interval. Actually, an absolute maximum, since we kind of already defined that whole interval. And now for the local minimum or absolute minimum, we just look for the smallest value that we have here. In this case, it's -1. That's the smallest one we have for our minimum, and our answer is A. Question 8, which of the following statements are true? So statement 1, square root of x has an absolute maximum. No, it does not, because square root of x looks like this, where it starts out at the origin and then continues on forever. And it goes on forever towards infinity, both horizontally and vertically. So because of that, it doesn't really have a maximum, because for any point that you take, there's always going to be a point that is higher up above it vertically. So square root of x does not have a maximum, so statement 2 is false. So what about statement 2? F of x equals x cubed. And from the interval from -3 to 1, it satisfies the requirements of the mean value theorem. So the mean value theorem, the only thing it requires is that whatever interval you give, it's both continuous and differentiable for all of those values. And x cubed definitely is. That's just the standard like cubic formula or cubic curve, just looks like one of those, and it is differentiable and continuous among any point that you give. So statement 2 is true. It does satisfy the requirements. Now what about statement 3? Rolle's theorem guarantees at least one value c between 0 and 1, where the graph of f of x equals tangent of pi of x has a horizontal tangent line. So basically, does Rolle's theorem apply to tangent of pi times x? And no, it does not. So what Rolle's theorem also needs is for whatever interval you give to be continuous and differentiable for all values among the interval. Now, it didn't really give an interval. This interval only applies to c, not x. So that's not what we're talking about. So I guess for this problem, the interval is the entire function from -infinity to infinity of tangent of pi times x. Now, tangent of pi times x is not continuous and not differentiable for any value among it. So tangent of pi times x is really just tangent of x compressed by a factor of pi horizontally. And tangent of x it looks like this. It goes like that, then that, then that, then that, on and on forever in both directions. And there are several points, several asymptotes that this function has where it's not continuous or differentiable. I believe it's at every pi over 2 plus pi times k, I think, where k is an integer. I think that's the fancy way of saying it. But there are an infinite number of values that you cannot plug into tangent of x. So tangent of pi times x also has an infinite number of values that you cannot plug into. And because of that, it is not continuous, and Rolle's theorem does not guarantee it. So that one is false. Our answer is answer choice B. Question 9, a certain function f of x has the following first and second derivatives. We've got f prime of x here and f double prime of x there. How many relative maxima does the original f of x have? Okay, so relative maxima, those are just the points where the graph has a little hump or a hill or a relative maximum value. So if we just kind of do an example function here, looks like its relative maxima are going to be at these 2 points right here, where it has a little peak. So those are relative maxima. Now to find it for this problem, we need to find f of x's critical points. Now to do that, we set 0 equal to f prime of x, and then solve for x to find those critical points. And fortunately, we are already given f prime of x. So we don't even have to find that derivative. We can just go ahead and plug that in and start with this. So we have 0 equals 3x to the fifth minus 6x cubed. Solving for x, it looks like first thing we can do is divide everything by 3. So we can do 0 equals x to the fifth minus 2x cubed. Looks like we can take out an x cubed from the right, and we'll get 0 equals x cubed times x squared minus 2. And then we can go ahead and break this off into two separate equations. So we'll have 0 equals x cubed and 0 equals x squared minus 2. We can just solve both of these independently. So on the left here, we'll have x equals 0 if we just cubed root both sides. And on the right, we'll have 2 equals x squared. And then square root of both sides, we'll have positive and negative root 2 equals x. So it looks like we've got three critical points. We've got 0, root 2, and negative root 2. So knowing that, we can go ahead and set up our little table to find out these maxima and minima. So we'll have x and, oh, this is actually, okay, this is going to be a little different. Normally, I like to do it with an f of x here. But unfortunately, we're not given f of x. We've only got f prime of x and f double prime of x. We could find f of x by doing some integrals, but we have not been taught that yet. So for this, I'm going to solve this problem using f prime of x, and we'll just, it's pretty similar, but I'll explain what we'll do at the end after we sort of fill out this table. So we do what we normally do. We plug in all of these values, all these critical points in ascending order. So at the start, we'll have negative root 2, then 0, then root 2. And then we fill in some easy intermediary values that we can plug into f prime of x. So looks like we can probably do negative 2, negative 1, 1, and 2. Those are pretty easy. Now, we do have quite a bit of outputs to compute here, but since these are pretty easy values, that shouldn't be too bad, especially because for a lot of these, we already know the answer to them. It's going to be 0. So if we just write zeros here, because that's what we found out in the original thing, we already have 3 of our critical points figured out. And then for the other 4, we can just plug them in. So plugging in negative 2 into f prime of x, we'll get negative 2. Looks like we'll get, okay, so negative 2 to the fifth is negative 32. So that's going to be negative 96 minus, all right, negative 2 cubed is negative 8 times 6 is 48. So negative 48 is going to be plus 48. That equals negative 48. We have that right there. For negative 1, so f prime of negative 1, we have negative 1 to the fifth is still negative 1 times 3 is negative 3 minus negative 1 to the third. I'm sorry, did I say negative 1 cubed first? It doesn't matter. It's an odd power, so it's still going to be negative 1. But this is going to be negative 1 times 6, so that's going to be negative 6. So plus 6, that equals negative 3. Put that there. And then positive 1, this is going to be, I think this is going to be the exact same thing, but with the sign flipped. So f prime of 1 is going to be just 3 minus 6, which equals negative 3. Oh, I messed that last one up, didn't I? It's supposed to be positive 3. Negative 3 plus 6 is positive 3. Okay, there we go. That's negative 3, and then for positive 2, f prime of 2, I'm pretty sure this is going to be positive 48, but just to make sure, 2 to the fifth is 36. 36 times 3 is 96. 96. And then minus, that looks like a G. Whoops. 96 minus 2 cubed is 8. 8 times 6 is 48, so that's minus 48. That equals positive 48. Awesome. So what can we do with all these values that we've just generated, that we've just plugged in and figured out? So since we plugged in all of these into f prime of x, what all of these tell us is the slope at that point. So if we kind of look at maybe these values here, it looks like it starts off, so at negative 1, it has a positive slope. At 0, it has a slope of 0, and at 1 it has a negative slope. So that's going to look something like this, where you have -1, 0, and +1. Looks like it starts off with a positive slope. At the middle, it has a slope of 0, and then ends off with a negative slope. And that is exactly what we're looking for. Look at the shape we've just drawn. This is a hill, this is a hump, and 0 is a relative maxima. So this is one of them that we're looking for. And applying this same logic to everything else, that is actually our only relative maximum. Because looking at these these two triplets of points, it is the opposite. So let's just take a look at the first one. We've got negative, 0, and then positive. That's going to look something like this, where it starts off with a negative slope, and then a slope of 0, and then ends with a positive slope. Those two triplets, those are going to be relative minima, which we are not looking for. We're just looking for a relative maximum, of which we only have one of, so our answer choice is B. And why did they give us f double prime of x? I have no idea why. Question 10. This is almost an exact repeat of the previous one, question 9. It has the same setup with the same first and second derivatives of f of x. It's just asking for a different part of it. So question 9 asked for its relative maxima, or how many relative maxima. This one is asking for how many inflection points f of x has. So inflection points are the points on which the slope of the function changes from decreasing to increasing, or vice versa. So if I were to kind of graph this out as an example, since that always helps, if f of x looks like, I don't know, something like this, whoops, like that, its inflection points would be all of these points there where the slope changes its direction. So you'll notice for this first one, the slope is it's decreasing. It's kind of going in a what do you call it? Not like clockwise, but just kind of a decreasing. I don't know the best way to explain it, but it's kind of going down at every point. But after this point is reached, it likes to go up after that. And the next one is the opposite. So before it's increasing, and after it's decreasing. So that's what inflection points mean. It's just when it changes from decreasing to increasing, or from increasing to decreasing. And in order to find those, we need to use the double, or the second derivative of f of x. The reason we need to do that is realize what happens when we go all the way there. What happens when we do f prime of x and then f double prime of x. So if we were to do f prime of x, the first one, this would look like something like this, where those 5 points just correspond to the relative minima and maxima of the first derivative. So at the start, we had the inflection points. And here, all of those 5 points, these are now f primes, critical points. So that is how inflection points become critical points. And we know how to solve, or how to find critical points. We take its derivative and then set it equal to 0. AKA, when we take its derivative, we just find its zeros. We have our function that's going to look something like this. Those are those 5 points, and they all lie on the x-axis. These are just f double primes, zeros. So that is how all these relate to each other. If you have f of x and you're trying to find its inflection points, first you find f prime of x, that'll be its critical points, and then f double prime of x, that'll just be its zeros. So based off of this, we can just go ahead and set f double prime of x equal to 0, and then solve for x, and those will be its potential inflection points. So that is why you do that when you find inflection points. So erasing, it's so sad I have to erase all of this. I liked that explanation, but I need room to do math. So 0 equals f double prime of x. That's going to be 15x to the 4th minus 18x squared. You just go ahead and solve for x. So looks like we can divide everything by 3, and we'll get 0 equals 5x to the 4th minus 6x squared. Looks like we can take a x squared out of both of these terms, and we'll get 0 equals x squared times 5x squared minus 6. Now we can break this off into two different equations. So we've got x squared equals 0 and 5x squared minus 6 equals 0. And we can just solve each of them independently. Yeah, this is unfortunate. I have to erase my work. On the left here, we've got x squared equals 0. We can just square root both sides, get x equals 0. And on the right, let's see, we can add 6 on both sides. So 5x squared equals 6. Divide both sides by 5. We've got x squared equals 6 over 5. And then square root both sides. We've got x equals plus and minus square root of 6/5. So there we go. We've got our three potential inflection points. Unfortunately, those are potential inflection points. Sometimes graphs are weird, and some of these inflection points aren't actually inflection points. We actually had to go ahead and do that back in question 9. We determined that there were three potential critical points, but we had to scrutinize further and see if those were minima or maxima. We kind of have to do the same thing here and figure out if these are actually inflection points. The cool thing is, though, this is the maximum number of inflection points that we'll have. So we'll have a maximum of 3 inflection points, so we can go ahead and automatically rule out answer choice E. So how do we go ahead and find out if these are inflection points or not? Well, remember back when I graphed earlier where you took f of x, x's inflection points and turned them into f prime of x's critical points? So what we can do is just find f prime of x's critical points. Unfortunately, these are going to be those critical points. So we can just go ahead and set it up kind of like what we did in question 9. We've got x and f prime of x at the top, and then we just go ahead and put all of our values and intermediary values in there along with their outputs. So we've got 0 in the middle, and then negative root 6/5 and positive root 6/5 above and below it. And then for values that go in between, root 6/5 is greater than 1, so we can go ahead and put negative 1 there and 1 there, and then it's less than 2, so we can just go and put negative 2 and 2 there. That should be pretty easy. So plugging these into f prime of x, we'll get zeros for the values that we've already. No, I'm sorry. We need to be doing f double prime of x because we went one step further. In order to find f prime of x's critical points, we need to find f double prime of x's zeros. So we need to plug all of these x values into f double prime of x, and that'll give us our zeros. So plugging all of those in, we get zeros for the points you already found out. And then for the other ones, plugging in negative 2 into this, so f double prime of negative 2, that'll equal, so negative 2 to the 4th is 16. 16 times 15 is a big number, but that number is definitely going to be bigger than whatever this is, because negative 2 squared is just 4. 4 times 18 is definitely going to be like less than 100, and this is definitely going to be more than 100. So because of all of that, this is going to be positive. And that's really all we need to know for these. That's basically what we just based question 9 off of. So we really can just use positive and negatives for all of these. So doing that, f double prime of negative 1, that's going to be 15 minus 18. That's going to be negative 3. That is negative. Plugging in a positive 1, let's see, f prime of 1, that's going to be also 15 minus 18 is going to be negative 3, so that's also negative. And doing f double prime of 2, that is going to be the same thing as f double prime of negative 2, since all of these powers are even. So that's going to make all of these positive afterwards, and the sign of x won't really change anything. So this is going to have the same answer, and it's going to be positive at the end. So based on all of these signs that we've figured out, what can we tell from it? Well, what we can tell is that this potential inflection point is bogus because on both of its sides, it's negative. So it's going to be something like this for that point, but we want something like this, where it's positive and then negative. So because of that, this inflection point is null, and we actually only have 2 true inflection points. So our answer choice is going to be C. Question 11. This is our first limit. I'm surprised. Usually I like to have a lot of limits on these. We've got the limit as x approaches pi of this big fraction. So immediately my spidey senses are going off. Whenever you have limits of fractions, usually how these go is you use L'Hopital's rule. So what L'Hopital's rule says is if you go ahead and plug in the value that x approaches, in this case it's pi, if you plug it in and what you get is 0 over 0 or infinity over infinity, you can do something special after you do that. I'll explain what that is after we go ahead and actually do that. So plugging in pi into this, we'll get cosine of pi plus sine of 2 pi plus 1 all over pi squared minus pi squared. On the top, we're going to have, okay, cosine of pi is -1. Sine of 2 pi is 0, and then plus 1. So that's -1 plus 1, that's 0. And on the bottom, we've got pi squared minus pi squared, that's also 0. Great, we're in a perfect position to do L'Hopital's rule. Now, what L'Hopital's rule says is if you have a 0 over 0 or an infinity over infinity, you can go ahead and take the derivative of both the top and the bottom, and your limit will not change. It'll still give the same output for whatever value x approaches. And usually after doing that limit, the usual culprit for these problems is the denominator evaluates to 0. And after taking the derivative, it'll usually just cancel itself out. Like it'll be, looks like after we do the derivative, it'll just be 2x. And after we plug in pi, it won't be dividing by 0 anymore. So that's what I mean by that, and that's how L'Hopital's rule usually works. So we can go ahead and find these derivatives and get our answer. So we're going to do the derivative of the top first. Derivative of cosine x, that is negative sine x. Our derivative of sine of 2x, that's going to be, we're going to have to do chain rule for that one. So the first step is doing the derivative of the outside, which is the sine part. Derivative of that is going to be cosine. So cosine of 2x times the derivative of the inside. The inside was 2x, so we have to multiply this by 2. I'm actually going to go ahead and put it on the outside here. And then we've got this plus 1. 1's a constant, so its derivative is just 0. And then on the bottom, we've got derivative of x squared, that is 2x, and minus pi squared, that is a constant, so that is also just 0. So now we've got our new limit, which is negative sine of x plus 2 cosine of 2x all over 2x. And you'll see once we plug in pi into all these x's, we'll no longer be dividing by 0. We'll actually get a tangible answer out of it. So doing that, plugging in pi, we'll get negative sine of pi plus 2 cosine of 2 pi all over 2 pi. Now this equals sine of pi is 0, so negative 0, plus, okay, cosine of 2 pi, that is 1, and then times 2, so that's going to be 2 on the top divided by 2 pi, that equals 1 over pi. Our answer is B. Question 12, based on the graph below, excuse me, what can we say about the limit as x approaches 1 of f of x divided by g of x? Okay, Jesus, I am burping a lot. I'm drinking a lot of water. I guess you could solve this problem by just figuring out the equations for f of x and g of x. That doesn't sound too particularly difficult because they give you some units to work off of. And you could just go ahead and divide f of x by g of x and figure out your limit. But what I am going to use for this one, I literally just found this off the internet. So if you have two lines that are being divided by each other, or you have one line divided by another line, and these are lines because they are straight, the resulting line is going to be, so let's say f of x divided by g of x equals h of x. H of x is just going to be a straight line, and it's going to be greater than 1 if the slope of f of x is greater than g of x. Likewise, it'll be less than 1 if the slope of f of x is less than g of x. So we can see here that because f of x is above g of x, it's got a greater slope. So that means that h of x is going to be greater than 1 at all times. So then our answer choice is A. Awesome.